This is the Ecoconcrete student competition for 2021. Our team is DurhaCrete. This presentation is by Mel Ken, Landon Marshall, Parker Warnicki, Blake Watson, Skylar Willard, and Kenny Z. Stratton. For the decision-making process, cost was a heavy factor. We looked at water, cement, coarse aggregate, fine aggregate, fly ash, class F, slag, and silica fume. Out of all of these ingredients, we used all of them except for silica fume, as it was extremely expensive and almost 2 times as expensive as just regular cement. Another factor was durability. We wanted our cement to last as long as possible with the longest service life. Another one was compressive strength. We wanted our concrete to be as strong as possible with the conditions already set. Finally, the environmental impact, as Portland cement accounts for 5% of the total global carbon dioxide emissions, which contributes to CO2 emissions turning into air pollution, climate change, acid rain, human health problems such as headaches. Therefore, the least amount of cement as possible is best for the environment. This being said, we wanted to use as much mineral admixture as possible. We used, as said before, we use slag and fly ash. Slag is a byproduct of the iron industry, and fly ash is a byproduct of the coal industry, and both of these are recycled materials that can be used in cement and concrete mixtures. The use of these materials cuts the amount of Portland cement to almost half of an ordinary mixture, and it prevents wastefulness and the spread of CO2 into the air. For the life cycle assessment, or LCA, we needed to monitor the carbon footprint of concrete batching, ozone depletion, carcinogenic, and ecotoxicity. Regardless of the durability, the effect that the creation of cement can have on the environment is a worldwide issue. The LCA was split up into 5 categories, which consisted of fossil fuel depletion, ecotoxicity, ozone depletion, carcinogenic, and global warming. Through the utilization of slag and fly ash, the ACS concrete mix was able to reduce the potential environmental impact by an average of 19.5%, measured across the 5 categories, which was the environmental impact score. Table 1 shows the characteristics of our base case scenario and our alternative case scenario mixtures, and Table 2 shows the comparison of the total emissions from the 5 categories. This is an additional figure that shows the comparison of the 5 environmental impacts. This is the travel map that was used in order to map out the locations where ingredients from the mixtures were collected. For the mixtures, our base case scenario and alternative case scenario had a WC of 0.4, which was a requirement. Base case scenario had 100% cement, while in the alternative case scenario, substitute cementitious materials were used. As said previously, fly ash and slag were used, 15% of which was fly ash and 25% of which was slag, and the rest was 60% cement. The batch measurements are shown below. For the base case scenario, 175 kilograms per meters cubed of water was used, 438 kilograms per meters cubed of cement was used, 1,075 kilograms per meters cubed of coarse aggregate was used, 600 kilograms per meters cubed of fine aggregate was used, 4.5% of air was included in the mixture as well. For the alternative case scenario, 165 kilograms per meters cubed of water was used, 263 kilograms per meters cubed of cement was used, 1,075 kilograms per meters cubed of coarse aggregate was used, 626 kilograms per meters cubed of fine aggregate was used. Air content was the same, staying at 4.5%. And the additives were fly ash, which 50 kilograms per meters cubed was used, and slag, which 100 kilograms per meters cubed was used. Any questions? We have answers.